Have you ever imagined a photon, a particle of light, leaving a material before it even enters? Sounds like sci-fi time travel, right? But in the quantum world, the impossible sometimes happens. Welcome back, wonderful person. You are watching Space 2 Theories, and if you love space, astronomy, and the mysteries of the universe, you're in the right place. Don't forget to hit that like button, subscribe if you haven't already. In this video, we'll dive into one of the most mind-bending experiments of recent years. How researchers observed what looks like negative time in photons interacting with atoms. We'll explore how this was done, what it means, and what it doesn't mean, so we don't get lost in sensationalism. Let's go. Part 1. The setup and basic idea. First, what exactly was done? A team led by Daniela Angulo and Ephraim Steinberg at University of Toronto and collaborators set up an experiment where a pulse of light, photons, passes through a cloud of ultra-cold atoms, rubidium for example. They asked, how long do the atoms remain in an excited state after interacting with the photon, and how does that relate to the group delay, the time it takes the pulse to traverse the medium? The key surprise: in certain conditions, the measured average excitation time was negative. In plain terms, the photon appears to exit the material before the atom enters the excited state, or at least the clock integral of events gives a negative time. Now, before you jump to conclusions, this is not sending information to the past in the usual sense. We'll get there. Part 2. Why negative time? Understanding the quantum optics. So why does this result appear? A few key points. When light pulses pass through a medium near atomic resonance frequencies, the refractive index becomes strongly frequency-dependent, dispersion. That gives rise to phenomena like group delay, the delay of the pulse envelope. If you choose a pulse narrowband and tuned near resonance, the group delay can become negative, meaning the peak of the transmitted pulse emerges earlier than you'd classically expect. In the experiment, the researchers probed the atomic excitation time via a secondary probe beam, using the cross-Kerr effect, which allowed them to measure the integral of atomic excitation and compare with the delay. They found the average atomic excitation time ranged from about 0.82 x T0 up to plus 0.54 x T0, where T0 is the characteristic non-post-selected excitation time. This suggests the label negative time isn't just a mathematical artifact. It has a measurable connection to physical interaction times in the quantum regime. Part 3. What this doesn't mean. Clarifying misconceptions. Because this sounds wild, let's clarify what this does not imply. It does not imply you can send information back in time or have a photon deliberately signal something to the past. The experiment did not violate causality or allow communication backward in time. The negative time here is about average excitation times or delays in a quantum ensemble, not a photon literally traveling back in time like in a sci-fi movie. The speed of light limit, from Albert Einstein's special relativity, is still safe. No information or signaling exceeded the limit. The photon behavior arises from quantum superposition, phases, absorption, and emission, and the definitions of time spent become subtle. Many scientists urge caution. Some of the headlines, time-traveling light, are provocative, but the underlying physics is subtle and still under discussion. Part 4. Implications. What's next? Why is this important? A few reasons. It deepens our understanding of light-matter interaction at the quantum level, especially in regimes of strong dispersion and near resonance, where how long does a photon interact with an atom becomes non-intuitive. Potential relevance for quantum technologies, controlling pulses, delays, storage of light, quantum memories, optical switching. The more we understand subtle delays and excitations, the better we can engineer devices. It raises fundamental questions about time in quantum mechanics. What does it mean for a particle to spend time in a state when superposition, phase, and measurement complicate the story? It may intersect with broader themes in physics like time symmetry, T-symmetry, causality, and the arrow of time, though those are big and abstract topics. For example, physics has the concept of time reversal symmetry, T-symmetry, which is broken in many real-world systems. As for what's coming, more refined experiments, perhaps different media, different atoms or pulses, different measurement strategies. It's a growing frontier rather than a closed case. Part 5. How to think about it as a curious mind. If you're a space physics enthusiast, here are some pointers to keep in mind. When you see negative time in a headline, ask what definition of time is meant. Excitation time, group delay, etc. Think of time spent as a statistical average over many photons, atoms rather than one photon literally going back in time. Recognize that quantum optics often challenges everyday intuition. Particles behave in ways that classical analogies fail to capture. Keep causality in mind. The macro world we live in still obeys cause, effect, even if micro world gets weird. Use such discoveries to fuel wonder, not confusion. They show that nature has richer layers than what we encounter day to day. So to wrap up, researchers have observed what appears to be negative excitation times for photons interacting with atomic clouds, a result that shakes our everyday notion of time, but doesn't break causality or enable time travel in the sci-fi sense. Instead, it underscores how quantum mechanics continues to surprise us. If you enjoyed this dive into the weirdness of quantum light and negative time, remember to hit that like button and subscribe to Space 2 Theories if you haven't already. Drop a comment below. What's the wildest quantum result you've heard of? Let's chat. Thanks for watching, wonderful person. Until next time, keep looking up at the stars and questioning the cosmos. Make sure notifications are on so you don't miss our next journey into space, astrophysics, and cosmic mysteries. See you in the next video.